Thank you so much for the introduction, Emmanuel. And again, thank you so much for the invitation and for having me here. So this is a project that I've been working on throughout graduate school. We got a paper out in 21 at VLDB. I gave an earlier version of this talk at my own seminar a few weeks ago, and I think some of the context didn't get through. So now we're actually just preferring to show instead of tell, because I think some of these things are pretty new or different from the way people might have expected it to work. So what I'm going to be showing you here is competition repository. So let me open the README. So here it is. So this is the Kaggle NLP disasters competition. So Kaggle is basically like undergraduate students can enroll, they get a data set. So in this case, it comes from Twitter, and they have some classification problem. So here they have to decide whether the emergency is real or whether it's just a figure of speech. So when we look at this tweet, it says that the sky is ablaze, but no one's in danger. So can we use NLP to figure that out automatically? So this is just a machine learning problem. We have the competition description that I've replicated in the README for my collaborators, and the data set that's available, as well as the schema of the data and other information. So I created this repository a few months ago, and I shared it with undergraduate researchers in the lab. And I asked them to get a high score on Kaggle. So basically, all you're doing is training NLP models, and you're trying to get a high accuracy, and you're trying to compete with other people, and just kind of do your own thing. And we've been using FLOR throughout to track things. So we're going to kind of like ask some queries on the exploration or on the past. So I can kind of showcase Hindsight Logging gradually. So you're looking right now at the demo Jupyter Notebook on VSCode. So I'm not using anything, all of these things are widely available. You've seen the README, and I'm going to show you some code. So I'm going to show you the training code, which is kind of like the main file of model training. This is what the code looks like. We have, what we're doing here is loading data. We define an LSTM, long short-term memory. It's an NLP model. We define an architecture. There's the training algorithm, which has like the stochastic gradient descent step and updates of the parameters. And then we have just the code in the end that invokes all of these functions and serves predictions. So I know that it's a lot of code. So I kind of have a canonicalized version on the left that I've highlighted. This is basically what deep learning code looks like most of the time. We have the train loader, the test loader, an optimizer, a network, and a criterion, a loss, which is a way of measuring the loss. There's a main loop that covers the full data set multiple times every epoch. And within that loop is another loop, the nested loop, which covers the data set batch by batch. We get the inputs, we compute the predictions, measure the loss to the ground truth, back propagate, send the gradients back, and update the parameters. And then we evaluate the model. So that's the structure of training. I've included some decorators that instruments the code for FLOR. So it instruments it for record and replay. So during record, the skip block is going to serve as a logging primitive. So it'll do the nested, it'll compute the full loop. And then once it exits from the loop, it's going to take a checkpoint of the network and the optimizer during record. On replay, they're parameterized differently. During replay, FLOR.it can use existing checkpoints to restore state. So if it wants to jump to epoch 50 out of 100, it can load the ending checkpoint for epoch 49 and then resume. You get parallelism by launching two jobs simultaneously. One covers ranges 1 to 49, the other one 50 to 100. And you can increase the degree of parallelism as needed. And the skip block can optionally skip the nested loop by loading the side effects. So this is just a memoization primitive. I'm kind of showing, I'm being very transparent about what the code is doing for record and replay. But it's also good to remember that it's not necessary to learn this new API. So FLOR is especially targeted for people who are learning data science and who might not do checkpointing. People who use TensorFlow and PyTorch already might already be doing some form of checkpointing, so they can incorporate these lessons themselves. But if you're a beginner, or if you're non-technical domain expert, maybe someone in biology or astronomy, then you want to make sure that your code is instrumented for fast record and low latency replay, even if you don't do any work. And that's possible because we offer an AST transformer. So here's the training data set that I showed you. And I'm going to show you what it looks like if FLOR transforms it for automatic record. What's a range of it here? The main loop is going to be of interest. So we see it's more verbose. It's not really human readable. It's made for the machine, but it still uses kind of the skip block primitive. I think one of the things that we focused on the paper was the side effect estimation. We used static analysis to detect the side effects of the loop. And here they are being produced. As you can see, it's an over approximation of what a human, a person, would specifically ask for, which is the model optimizer and CLR schedule. So we will continue the talk with the API mode, personally, because I prefer it. And it also allows us to cover some of the technical details of FLOR. And the way that you would transform this code is you would call a FLOR function at the beginning. When you do import FLOR, it can automatically transform the repository. And you will see some examples of transformations in this talk too. And as far as not slowing training, having low overhead, here are some numbers. We measured each name on the x-axis is a different experiment. So RTE is recognizing textual entailment. It's a fine-tuning job, and it's part of the general language understanding and evaluation benchmark. Then there's ResNet, Jasper, ImageNet. These are classic model training jobs, and they run for a lot of hours, 15 to 20 hours. And this is like 10 or 15 epochs. So these are very heavy models. And we won't be too surprised, right? If the checkpointing that we're doing is a net and optimizer once an epoch, we don't expect the overhead to be very heavy. So that's kind of what we're seeing. And next, so now we know that Alexis, the undergraduate, has instrumented her model training code for FLOR. And now we want to start using FLOR to answer questions about what she's done in the past, what worked, and what we should try next. So model developers iterate quickly to try many ideas. And we want to store every version of model training that was tried. And we do that by auto-committing. So we'll show you the timeline. This is the Git log of the current branch. It's too big for here, so we're going to open it on the side. And look at these automatic messages. Right, so FLOR is commit. Every time you run this train RNN, it's going to commit its version so that it's saved for posterity. And this is kind of intermingled. You can see here that I did a pull request. So I merged Alexis's explorations. I think she did like 100, and I collapsed this into a single commit, and I brought them in. And then there's also some commits that are manual or human initiated. So I think one of the things that model developers, one of the comments that they made was that they didn't want us to litter their Git repository with like automatic commits. So that's one of those things that we have to be very respectful of. So FLOR has as a safety, it makes sure that it has its own dedicated branches where it auto commits. And the idea is that we auto commit in this exploration branch. And when we're done with the exploration, we merge that back into the main branch, the single commit. But we're not just merging in code. We're merging in data and metadata and the whole history of executions. So this is kind of the context of machine learning. So we're going to explore the model training history next. I know I'm moving fairly fast. I can also pause for a minute if someone wants to clarify or ask any questions.
Are there any questions? Any questions? I think it's fine. Thanks.
Okay. So here I'm checking that I'm in the right repository, Kaggle NLP disasters. It's what you're looking at. I'm importing FLOR, a visualization library, Plotly, and NumPy, standard libraries in data science. And what I want to see is the fact table with all the data that was logged so far. So here's the raw data frame. We see that there is an optimizer, a learning rate, average valid loss, and a value. So what is this data? Each row was generated by a logging statement. So you see this logging statement that says average train loss. One of these executions contributed one of these rows. So that's what this information is. It's just logging. It's stuff that's been logged in the past. But now I can kind of start probing the values that Alexis retrieved when she was doing her explorations before. I do a projection so that I can focus on the timestamp, the epoch, the step, the name, and the values. And then I'm going to take that data frame and I'm going to separate it into data frames for record, which is the first pass of model training, and then replay, which corresponds to the hindsight logging executions. And what I'm seeing here, what I'm showing you is the names of the stuff that's been logged before, basically what's available for me to query. I see that there's the loss. And then on replay, I've also asked about the optimizer, the learning rate, and so on. So in the next step, I am going to plot the training loss over time. So as I move away from the origin on the y-axis, sorry, let me just correct that. The date gets later. So it's later in February. And as I move away from the origin on the x-axis, it's later in the number of epochs. The number of epochs grows. It's the loss that I'm plotting, and so lower values are better. Okay. And this is basically the blue and red executions. That's what like a normal training run looks like. The loss starts high, and then as the model learns, the loss decreases, and then it converges. So that's a very well-behaved step. We start to see that there's like some qualitative differences happening on February 9th. February 10th is all over the place, and then it has these two executions that when the loss is exploding like that, that's a bad sign. It means you're not learning. It might even be a problem of too high of a learning rate. So I'm already starting to kind of form theories about what might have been going wrong. And that's actually what motivates hindsight logging. So I see that the loss is exploding. I'm not sure why it's exploding. I want to know the learning rate, but I haven't been logging the learning rate. And let me show you reasons why the learning rate might be overlooked. So when Alexis started, she was using just a regular 0.015 learning rate with the Atom optimizer. And I've introduced a cyclic learning rate scheduler, which is a learning technique from Archive. And so before it wasn't relevant to log it, but now we want to keep track of the learning rate because it changes almost on every epoch. So I can insert the additional logging statements to track the learning rate. And I want to do replay in the past to see what that value was. Here, I'm also going to show you what's the difference between validation loss and training loss. This is a proxy for overfitting. So here we see that the training loss far surpasses the evaluation loss. It means it's not learning anything. And here we see that the training loss is decreasing very much, but the evaluation loss is not decreasing in the pink. And so that's a sign of overfitting. So that's another execution that we might want to probe. Okay, so this is the current version that I'm showing you, highlighting here. And I can just show you some hindsight logging. I don't know what might be a good thing to log. Are you all, do you all train models? Is there some value that you would like for me to fetch? Not, I can pick. Okay, so I will do like a print statement. And you're seeing me type this. And then I'll see the epoch, so we see a change. I come back to the Jupyter Notebook, and I call Python on this script, and I just say that we want to run in replay mode. So this is a model training run. It's using deep learning. It's running for 80 epochs. So we want to avoid the nested training loop if we want to print this information. And so what this is doing, we're entering the for loop, but we're skipping the nested training loop because we have a skip loop. We've memoized in the past. And instead, when we exit, we load the state of the model, we load the state of the optimizer, and we load the state of the CLR scheduler. And so we're actually generating output and measuring evaluations, but we can avoid training the model completely. So I'm going to remove that print statement. And then we can do some hindsight logging of an even earlier version. I'm happy with the optimizer and the learning rate. Let's see if there's more information that I could log. I might want to log the device. I'm asking here about the versions that I've replayed before. So there's the replay data frame. There's the learning rate. I'm asking, because I know that the learning rate only appears in replay, I can use that as a proxy for narrowing down my focus. I'm checking the timestamp and I'm checking the unique values. So let's map that back. So the green one was interesting. It's on February 10th at 3:29. That's something that I logged, that I hindsight logged last night when I was giving this demo to my wife. So instead, I'm going to show a different version that I have never seen before, which is February 10th at 3:25. So 3:25, I haven't probed that yet. Okay, I don't think I need this. And then I'm going to propagate the logging statements back in time. So I know that it's going to be on the 10th. And it's 3:25. There we are. And I select this value. And so now you're going to see me do logging statement propagation. So I'm going to send the logging statements back in time historically for replay. So what I'm doing is I'm staging the train RNN file so that FLOR can scan it and it can collect the logging statements that we want to inject. It's staged. Now I'm going to check out the version D99, which is the one that is presumably overfitting. Save, okay. Version control. I do want to save my notebook. And that one's staged for the replay.json. I don't need this. And then train RNN, open. Okay, let's try that again. Just wrangling Git right now. Okay. Now I switched branch. So now I'm back in time. This will change. So you see that there's no logging here. Before we were logging the optimizer, that's not logged. There's no logging of the learning rate. There is some logging of the average training loss and the average validation loss. So what I'm going to do now is propagate the logging statements from the past into this current version. What did I do wrong? Aha. Okay, so FLOR found the logging statements at line 195, 196, 135, 22, and 220. And we see that the logging statement is inserted for the optimizer, and it's inserted for the learning rate. And even the weird one that I almost made a bug with on, that also got inserted to the device. And so now I replay. And again, when I'm replaying, I get to skip this nested loop. There are times when the model developer will ask for information inside this loop, and we won't be able to skip it, and we'll have to step in. In those cases, we parallelize so that each worker does one epoch of work. So this is where we can do sampling, approximate query processing, all these different techniques. Okay, so now I'm going to go back up and show you the record DF and the replay DF. Because I added a logging statement for the device that had never been logged before, we should see that appear here if everything went well. And it's there, right? So this is like new information that I acquired. And now I should have the learning rate available for that date, the February 10th at 3:25. So now that I have the learning rate and that additional information, let's go plot it. These names are confusing, but let's see. T-stamp epoch. Okay. So here we see that the earlier run on February 8th had a static learning rate, February 7th, sorry. The value was 0.0015. And later I was using the archive technique with the cyclic learning rate. And so the cyclic learning rates that peak at 4, which is at 329 and 331. So let's go see how that performed. $329, 331 is purple. There we are. That's the purple over here. So the purple execution is going to be much better behaved, and the pink one corresponds to the 325. I think that's the really high one. 325, the red. So that's what happened. I set the learning rate much too high. I think the peak was at 16, and so the model just failed to learn anything, which is basically what we said. Okay, so the next parts to this demo would be showing you query capabilities. That's actually what I'm working on next week. But I timed out, so this is as much as we did, and so some of it had to be a little bit more manual. But I can still give you a sense for what the idea or what the goal is. So first, I can show you this FLOR directory where we store metadata on each experiment. And you can see that what are these files? These files are indices to different checkpoints, so that as I jump around with FLOR, I can load those checkpoints. I have the actual pickle files, which is the information that was serialized in data. That's a lot of information. Let me try to see how big this directory is actually. It's 400 megabytes. It hasn't grown out of, it hasn't grown disproportionately, but these are all models and optimizers that I've been checkpointing in the past. And so this is kind of where you start getting into like, there's a lot of data, there's a lot of metadata, it all has to get managed. So this is MLOps. We think it's a databases problem. It's a data management problem for sure. And then I have the replay JSONs. There's the repo, the Git repository that also gets stored here. And then there's transformed files. So I can transform the full history to inject the logging statements and then do replay. So the challenge then is when I have VID timestamp, when I have all of these versions and I would like to select a query, I don't want to check these out manually. So once these loads down here, I can add a query. Okay. Sorry, drop duplicates. I struggle with pandas, but I'll write a SQL query next. So we see that we have all of these versions. What I would like to see is something like I select and then I choose learning rate. Okay, so I want to know what the learning rate is. And I want to know the optimizer that I used. And then from the name of the experiment, which is Kaggle NOP disasters. And so just by saying this to FLOR, it should find that the information that's requested does not require us to step into the nested training loop, so we can skip. The execution engine will do that automatically. But we might want to filter even further so that we're not executing every version in history. Like, we might be interested in the ones that showed anomalous behavior, and so we want to characterize that. So that's easy to slice. The diff is greater than something. Here, it's like for executions where the loss exceeds 0.8. Does that seem like a fair threshold? We slice it up and then we re-execute twice. So where are you loss? Average train loss. Greater than or equal to 0.8. And that would have produced what I showed you manually. And then the plotting is kind of separate. So that parsing and doing these steps automatically is what's on the to do next. But that's kind of, so the title of the talk of like querying the infinite metadata. So we're asking about derived information. We're virtualizing the trace. So any value from the execution in the trace is fair game. But also there's derived data and derived metadata. And you can never really know what's all the information that you might need to know about a model training execution until you need that information. So we make it possible to insert logging statements into the latest version, send those back in time, and then query to collect the information and answer your questions. I believe that's the end of the demo. I can use the rest of the time to have a conversation, answer questions, and I also have some slides in the paper that I can refer to if you're interested. There's the tensor histograms. In order to get the tensor histograms you get from reading the model, and you can get those at any frequency. Images and overlays are common in explainability and fairness. This is where people will highlight the areas in like the dog's ear that the model is picking up on to make the dog classification and so on. And so what we talk about is the reason why we motivated or started to work on hindsight logging is because in the lab, we saw that most people log the training metrics by default every time. And they wait for something to go wrong before adding logging statements for histograms and images and overlays. And that's because logging this information adds a lot of overhead. It can really slow you down. I think 4x, 8x slowdowns are typical because to get this information, the tensor histograms, you need to move data out from GPU memory into DRAM so that you can manipulate it and then send it to disk. So that's something that you can do only so much. Also in machine learning, exploration efficiency is first class. Most people don't, I feel like people retrofit the explanation for why something worked. Like they try a bunch of things, something happens, and then they come up with a theory post hoc. In advance, very few times people kind of like know that something's going to work. And that's where it's like machine learning is less of a science, less engineering and more, less engineering and more science, because it's very empirical, very trial and error based. And so I showed you that we have a Python file that gets fed into a GPU. Then you see some loss curves that don't make a lot of sense. You add more logging and then you replay. And FLOR wants the replay to not take as long as the first pass. So we can do it in 2 minutes instead of 7 hours, and that's recovering all the information, assuming parallelism. And so why this is hard, this will be the slide where I cover just about everything. So there's kind of like the part 1 from VLDB, where we want fast replay. And we achieve that by doing the least work necessary, which is skipping irrelevant code. You saw that with the skip block. And don't duplicate work, memoization. we also want to do that least work in parallel, and we can parallelize sequential code because we have these checkpoints that break cross-iteration dependencies. So model training replay is embarrassingly parallel. And I think in the evaluation, we evaluated on like a 16 GPU machine. Then, and because it's embarrassingly parallel, it doesn't require coordination. So the GPUs don't have to be on the same machine when you're doing replay. That's a huge benefit. For selective checkpointing, which is keeping the overhead low, we balance replay latency and checkpointing overhead with physiological logging. So with physical logging, we write some program state to disk. This would be like the network state, the optimizer state. And with logical logging, that's like saving the files in the Git repository for future replay. And one of the collaborations is doing background logging. So using a separate core to serialize and write to disk. And then we just have to worry about like, how do you protect the data from destructive operations? And then in Python also, because of the global interpreter lock, we can't do like true multiprocessing. So we use fork with copy and write as one-shot, one-way IPC for background logging. And we do everything we can do everything automatically with program transformation using side effect estimation. So that was another piece. I think you have intuitions for how the parallel replay works. Linear speed up for fixed cost. So it's embarrassingly parallel. It's ideal parallelism, actually, because as you add, when you add 4x GPUs, it gets 4 times faster, right? And so in EC2 and AWS, the cost breaks out even. So even though my time is getting shorter and shorter and shorter, I'm not spending more money. And I think what Benoit says from Snowflake, this is a quote from my advisor, Joe, that he's the one who remembered, is that in the cloud, fast is free. So background logging, we can go into some of the details. I think this plot is interesting, the training time in minutes for synchronous versus asynchronous logging. I showed you some images of the tensor histograms earlier. If we log those tensor histograms 4 times per epoch, that's not that frequent. It changes the training time from 18 minutes for this experiment, I think it was ImageNet, to 50 minutes for training. So it's like a huge explosion. That's kind of why the hindsight logging is typical. The auto record, which is the transformed recording script, does as well as the hand-tuned API, and which is, you know, negligible overhead compared to no checkpointing. And so this is kind of like the figure for hindsight logging, where even if training takes 7 hours, we take checkpointing so that it doesn't take much longer than 7 hours. And then on replay, we can bring that down by adding additional GPUs and skipping code. The talk that you just saw, these slides focus on replaying the latest version. It's like replaying one version of the execution. And the current work that I'm doing is extending that across time so that you can see how things change. And then logging, when I'm logging a single version, I can print to screen, I can dump it to a file. But when I'm recovering all of the files from every one of the 130 versions, that doesn't scale well, right? So now we get into like a scaling issue where I don't want to log 100 versions of code, and I don't want to scan through 100 different log files to understand what's happening. So this is where we're starting to see a database emerge and the need for query support. So that's what I'm working on right now.